This presentation is delivered by the Stanford Center for Professional Development.
So I've been hanging around Stanford campus since I was a kid. There may even still be bookcases in the Dean of Engineering's office that I built when I was in high school or something, when I was working for one of the labs over there. And but when I went off to undergrad, I went to Oregon State University. Great program there in mechanical engineering. But one of the things they didn't do very well at the time, I don't know if it's changed, I hope so, was there was not a lot of hands-on work in the shops and labs and that sort of thing. So I ended up having to get an art minor just to get my hands dirty. So I did a couple of years doing metalsmithing and jewelry work as part of my undergrad. And then when I got out of school, I went off to Lockheed, which if I had learned my lesson from undergrad about getting my hands dirty, I wouldn't have gone there, because I spent the next 10 years doing simulation and analysis work and giving presentations at the Strategic Defense Command in Huntsville, Alabama, and places like that for a long time. And I missed that so much that I eventually abandoned that career completely and came back to Stanford to make stuff, because I really enjoy making stuff. So with that, a couple of years ago, I was asked by the science teacher at our grade school to give okay. Now I really need to pay attention to what I'm doing here. The science teacher at our local grade school asked me to give a little quick talk at the science fair. So I did that. Come on, computer. Now, we don't have an aspect ratio problem. Oh. All right. Hold on. We'll fix this. Yeah, I have an aspect ratio problem with this mismatch between, yeah, maybe if he's got any thoughts, I should have done this beforehand, obviously. What do you think? Will this take care of it?
Yeah, you just have to...
What's the native for that one?
I think it's 1280 by 960.
Okay. Cross our fingers. Is it coming up there?
Well, David's fighting this nightmare. How many of you actually are in a similar boat?
It's not
you don't
coming
get to
up.
build stuff that you wish you did.
Try just in the photo.
Oh.
Try to make sure that's in there.
It's not happy.
Try taking it out and put it back in.
Oh, okay. This is I remember when I was at Lockheed all those years that the standard for presentations and the like was viewfoils on a viewfoil projector. And the only thing that ever went wrong was the bulbs always burned out. And it's still not coming up.
Mess with it a little.
Yeah, please.
Wait, scroll it.
Ah, there we go.
That's square, yes.
Okay,
Try.
let's try. That is my other car, which does not classify as a fuel-efficient vehicle.
Or you try dragging it. That vehicle.
Yeah.
Try to attack
There we go. Now I actually have to, yes, lovely mouse. Get it? No. Come on. Right after this talk, I'm taking this computer to, I actually am, oh, it's coming back to the, it wanting to default onto the wrong screen.
You can just mirror displays.
Yeah.
How do you is this slideshow?
Well, now it's not letting me even. God, good grief. My favorite. Okay, that's gone back to a single display.
Well, we can also ask, has anybody who wanted to read cold cash, cold climate not gotten hold of a copy?
Okay.
This keeps showing up. It's showing up great on my screen, so I can give this whole talk. You just won't get to, yeah. You just won't get to see it is all.
Go down to the bottom of the.
Oh, and I actually got a cursor back. That's a sign. It's doing, it's.
Good.
So I spent about 10 years at Lockheed doing ballistic defense stuff, and then came back to Stanford to do a couple of years in the graduate program and in the design program, which was awesome. I had so much fun. And when I left here, I spent a couple of years working for a company down in Los Angeles, Wet Design. You may have heard of them. They actually were founded by another Stanford grad who did the product design program, Mark Fuller, because he really liked fountains and water. So I spent 2 years down there working on, genius. Woohoo! Yes, a hand for that man. Okay, great. And then after a couple of years working on fountains, the one that was really memorable, most of my time there was spent working on the Bellagio fountain, which I'm sure you've all seen, and every television or movie always seems to start, if it happens in Las Vegas, starts with a shot of that. And then I went off to Xerox PARC, where I worked on robots for a while. So this photo was taken in the loft space, the old design loft space that is by the mechanical engineering shops when I was working on a light sculpture back in the mid-90s. And one of my projects for my graduate, actually this was more like avoidance of working on my projects I was supposed to be working on. I made an ice cream maker. And this is a couple of projects that I did as part of that master's thesis work on cups. I just did an exploration to a bunch of different cups. This is hand-raised silver. I don't know if any of you have ever seen this kind of work before. You start with flat sheet metal, and you start hammering on it, and eventually you raise up this form, which can then be, in this case, soldered to a lost wax cast stem and polished and all that sort of thing. And then these were, I was really proud of these, especially recently. These are sort of stemless stemware, which I've noticed over the last couple of years have actually been in stores. I can say that I actually built some back in 1995. I didn't make any money off that though, so this is not. This was the tea set I did when I was in undergrad. It was when I was trying to get my hands dirty and avoiding my mechanical engineering homework. This was the Bellagio fountain when it was when there was no water in the lake. So this lake is about 10 or 12 acres. This would be sort of the opposite of the environmental project, because this thing consumes massive amounts of energy, right? It's got 3 megawatts of light fixtures in it, and it spends all of its time pumping water into an arid environment, right? So maybe not the most environmentally conscientious thing to be working on. It's very cool. It's an awesome display, but when you start thinking about the stuff underneath it, you just got to shake your head. The other project I work on when I was at school was this robotics project that was also great fun. And when I got out of grad school, I got done with working at the fountain company. I went off to work at Xerox PARC, where we were working on these modular self-reconfiguring robots. These were a blast. Very, very cool and interesting projects. Lots of opportunities in that space in robotics for our future. The one that comes to mind today, just because of my involvement with Tesla, is the self-driving automobiles. The impact that will have on our lives and our environment in time I think will be really dramatic, not just for the lives saved, but also there's great opportunities for increases in efficiency and that sort of thing. Imagine you're going to Grand Canyon for your weekend or for your week off or something like that, and you could just sort of crawl into the back of your car and snuggle into your pillow and sleeping bag and tell it to get there around 8 o'clock in the morning and stop for coffee when we get there, please. And you only have to drive 25 miles an hour, which is the maximum efficiency speed, so you can save a lot of energy on the way. So this is sort of the work that I did before I started at Tesla. These robots, they actually did stuff. Each one of these little robot modules were the same. So they could all sort of not each do very much, but you put them together in different configurations and they could do interesting things. Oh, and this one, I think, this never works for me. So if it would have worked today, I would have really been stunned. Let's see here. Oh, now my other folder got shut off. So courtesy of our computer issues, I'll work with my... You ever have those days where you worked out way too hard the day before and then you went out drinking late and then you had to get up early the next morning? This guy. It's a slow process. But the beauty of robots is that nobody has to watch, right? We watch them because they're interesting to watch, but for the most part, they can just do their own thing and take as long as they need to, because eventually the job will get done. Those were a blast. All right, so that's where I've been. Let's talk about where I am. So this is actually my favorite slide in the whole presentation. It's not mine, of course. Lawrence Livermore has been cranking these out. I hope you've seen this slide before, actually, because it's one that it has so much. I mean, Edward Tufte would love this slide, right? It has so much information on it and tells all kinds of different stories in it. One of the stories it tells is what we do for transportation. How do we get from place to place? What do we use to get there? And there's really only one thing. We use petroleum fuels. That's it. There's a little bit of, some other stuff, biodiesel and natural gas and biomass. But for the most part, it's all petroleum. And in fact, it's very hard to do anything but, right? fuels are just such an efficient carrier of energy that it's very difficult to do anything else in the transportation sector except use some sort of fuel. The other story in this chart is about how efficient these processes are, right? So you look at the backside of this. Now they've just made an assumption down here about the efficiencies of various processes. So there probably ought to be error bars around all these things. This chart assumes that the fuel use in transportation is 25% efficient. I think that sounds like a good number. Every time I've gone out and looked, those are the kinds of numbers you see. It's hard to do better than that because there's so many constraints on an engine in a car, right? It has to fit into a certain volume. It has to fit into a certain weight. It has to fit into a certain cost in order for it to work as a prime mover for a vehicle. That, you know, efficiency is only one piece of that total puzzle, right? If you look up at the top, though, in the electricity generation, there's a couple of things you see. One is that there's any number of fuels will work for that sector. You can generate electricity with almost anything. And the processes for generating electricity from a fuel, for instance, are inherently more efficient. Why? Because that's really the only thing they have to focus on. Aside from, I mean, obviously there's emissions and all that sort of thing, but they don't have weight constraints. They don't have to lug these things around. Cost constraints are much looser just because you've got a power plant that's going to sit there for potentially decades cranking out energy. And since the primary cost of goods sold to a power plant is the fuel that fuels it, you want to use as little of it as possible. So there's a huge incentive for them to make that process efficient. So if you can divert some of this electricity down here into your transportation, you've accomplished a couple of things. One is you've reduced your dependence on this one particular class of fuels, and you've put yourself in a space where you can do something more efficient because you can separate the operation of that vehicle from the efficiency of the power generation you're using to drive it. So, but there are, of course, challenges. But before we get to those, talk a little bit more of this. So, start with 1.5 gallons of gasoline. Why 1.5 gallons? Because that's roughly equivalent to 56 kilowatt hours, which is the amount of power in a Tesla Roadster battery pack. Which, right off the bat, tells you a whole nother story, right? $5 gas can with a little bit of gas in it, weighs this much. 56 kilowatt hour battery pack, that's, you know, really big and costs tens of thousands of dollars. So there's clearly some work to be done there. But this thing, of course, is used over and over and over again. And the efficiency of the process in the electric vehicle is very high. Conversion from battery through drive electronics into motor out to wheels is in this kind of 80% class. Whereas for 1 gallon of gasoline, most of it goes out of the tailpipe, the rest of it goes to your wheels. So just looking at the sort of carbon footprint and dependency on petroleum fuels, even the most efficient vehicles, you know, in this class are obviously using oil, using gasoline. Their emissions are generally higher, partially. Now this is actually maybe the plus side of expensive battery packs. If battery packs were cheap, you wouldn't necessarily care how big or efficient the car was in terms of how much energy it takes to push it through space. But because battery packs are expensive, there's actually a really strong motivation to make them as small as possible, which pushes you to reduce the drag, reduce the weight, make your car as efficient as it possibly can be, so that by the time you do put that expensive battery pack in it, it can be as small as possible. So here's some comparisons of, right? So we've been talked about sort of how efficient the car is from taking power in the battery to the wheels. Well, okay, but that doesn't really tell the whole story of getting that fuel to the power station, through the power station, through your electric transmission lines into your car. When you take it all together and just do what they call the well-to-wheel energy calculation, which I presume a lot of you have seen before, something like the Roadster, and actually really any all-electric vehicle is going to fall over into this category. Maybe not as great as the Roadster is, but they're going to be over there just because of the efficiency of getting power from a power station as opposed to generating it yourself in your car, and the drive to make the electric vehicles as kind of efficient as they can be for the payload they've got to carry to keep costs down. So where are those costs coming from? Well, right now they come from two categories, and those, both of which have huge opportunities to change. The biggest contributor is the actual cell itself. Turns out, and I don't really understand the whole story, but I'm guessing that all the laptops in our laps and on our desks here have driven the development of this particular cell, this lithium ion 18650. It's 18 millimeters in diameter, 65 millimeters long. It's a single cell that gives 3.7 volts or whatever it is nominal, and anywhere from, a few watt hours, maybe up to as many as 10 watt hours or something like that. They are, for your money, the best deal in town, except for lead acid. But I think everybody, right? There's not a single car out there, except if you go to a sort of obscure build-it-yourself site that uses lead acid battery packs for vehicles. The only vehicles around that use those are forklifts. And they use them because they needed ballast weight anyway. So putting 1,000 pounds of battery on the back of this thing just to hold it down is a good thing. And they also, for the dollar, they deliver a lot of power. But these lithium ion cells are the next best thing, or actually, well, they're certainly the best thing in terms of for vehicle use. The other big cost, of course, to a battery pack is all the ancillary stuff. So when you take a bunch of these cells and put them together, lithium ion cells, they need to be monitored. You want to make sure they're balanced. You take a stack of cells, our battery packs in the Model S, for instance, is close to 400 volts. It has almost 100 bricks, we call them, in series to stack up to give you that 400 volts. You want to make sure that none of those little bricks get out of whack, that for some reason, if there's some, maybe one of the cells has got a little bit of a short circuit in it or something like that, and it slowly draining off the power in that one little brick for all those little cells in parallel. You've got to monitor the voltage on each one of those bricks. So you've got 100 bricks, well, then you're going to need 100 voltage sensors keeping track of all that stuff. These things are sensitive to temperature. We've all heard stories about them, even in laptops, but in other places as well, going into thermal runaway. So you want to monitor their temperature. You want to watch them. Even your rechargeable hand tools have, 3 leads on every battery pack, 2 for the actual charging and a third one for the little temperature sensor that's in there to monitor their temperature. So there's lots of management that happens. So inside a Roadster battery pack or a Tesla battery pack, there's what they call a battery management system board, one board that kind of takes responsibility for the whole pack. And then there's another board for every one of these modules, and it has all the little temperature and voltage sensing lines going out. And actually that architecture is not unique to Tesla. Most everybody who's building, these days it's great. You can see lots of people who, cut open battery packs and look what's inside and post videos on YouTube. And so you can go look at and see how everybody else has solved this problem, and they're all sort of solving it in the same ways. They have the BMS board to take care of the whole thing, and then these little BMBs that monitor individual modules. People use different approaches for cooling. Some of the packs are very low density and they blow air through them to keep the temperature down. We use liquid cooling, circulate a coolant, basically like the fluid in your radiator, through the pack to keep them cool, or to, I shouldn't say not just keep them cool, to maintain their temperature. There's cases where we actually heat them up because they have a preferred temperature operating range. If you live in Minnesota or Alaska and leave your car out overnight, it's actually more efficient to waste some of the energy in the battery pack to heat the whole thing up so that you can use the heated pack up for driving. And there's news, it seems like every week, about another new battery technology and how people are moving forward in this. There's tons of room for growth in this area. There's also tons of room for growth in this space and the enclosures and the management systems for all that. Lots of work to be done. Some examples of cells that are out there. We've measured, if there's somebody out there making an 18650, we've put it on our testers and run it to see where it falls in terms of energy density. And you can see they're averaging about 200 watt-hours per kilogram. 200 watt-hours per kilogram. So what does that mean in terms of a pack? So when you take packs, and this is, I don't know if this is even a real number. I mean, we talk about this number. People sometimes talk about these numbers and compare, but in reality, if there was any kind of competition around pack power energy density, then it would stop mattering because people would arbitrarily move things in and out of the packs because you can do that. It's mostly, it's structure, it's electronics, it's cooling system, it's dead space. But these packs all run in this, so you've gone from a cell at 200 watt-hours per kilogram to a pack, which is something, order of half that. The Model S is in that sort of 140 class. So it's high. Partially it's high because it's large, right? The bigger you get, the less the overhead is for a given size. So the Model S is a big 85 kilowatt-hour pack. So it has a higher density than a lot of these smaller ones do. Okay, so got all this work, right? Figured out that you could build an electric car, it's gonna do all this stuff, but you gotta sell it on the market. What's it gonna cost? So if you start with, one of these cars, and then you make some admittedly gross assumptions, right? This is back of the envelope stuff. You say, well, I'd guess that maybe 60% of the purchase price of the car is everything but all the stuff I would take out if I was going to convert it over. And then I'm going to put back this other stuff, of which the battery pack is by far the biggest component. Let's assume that it's $600 per kilowatt hour. Now you take a car, take one of your cars, the compact, the sedan, or your sports car that has a base price of one of these numbers. Assume that your car can go 4 miles for every kilowatt hour. You're paying $600 per kilowatt hour battery pack. That's $150 on your purchase price for every mile that you can drive that car. And then you can see really obviously why the Nissan Leaf, for instance, has a short range, right? You would not take a $15,000 car and put in a $50,000 battery pack. Nobody would buy it, right? It's kind of like buying a $100 million house that's on a $100 piece of property. It just doesn't, something wrong about that equation. And so as you move up, and you understand then the motivation for Tesla getting started at this really high end. Because at the time they started, they probably couldn't have even produced a battery pack for this cost, much less made any money selling a small number of vehicles for $20,000 a piece. So they started way down here, in the $100,000 range. But it also shows you that what happens over time is, well, if the more you can drop that cost, the more those battery packs and electric vehicles make sense for more common, less expensive vehicles. So here's some examples. So if you start at $450 per kilowatt hour a battery pack, well, then your battery pack is just going to cost a lot. And in fact, this number is close to what the Model S, I think if you go online and look at the Model S battery, or go online to the Tesla website, they actually show you the purchase price of the car with either the 85 kilowatt hour, the 60 kilowatt hour, or the 40 kilowatt hour battery pack. And it's like a $20,000 difference for 45 kilowatt hours of power, which is not that number, but it's something in that. I'm getting my numbers mixed up. But I believe this number is close to what the Model S is. And this is similar to what the Model S range is, about 4 miles per kilowatt hour. So if you buy the one that has 300-mile range, you're probably spending, close to $35,000 on the battery pack. But as you develop cars, as you develop better technology, for the batteries and bring this cost down to 300 or 150, then all of a sudden these numbers start coming way down very quickly, and they make a huge difference to the purchase price of the vehicle and make those cars a reality. So the folks who founded Tesla did all that and decided to start a car company. And this was their first mule. I was trying to even look up what this vehicle was. I'm not even sure what it is, but it's boy, I'm sure they're glad they didn't go to market with that.
It's the body off the Lotus.
Yeah, it's the one that they actually used for the Roadster is very similar to the Lotus Elise. Doesn't look a lot like, it sort of looks like this, but oh, that's an interesting thought. Maybe that's where they got that. Anyway, that one had some great properties too. So they built their first mule. They got into the business. They had, I think, the company was founded almost on this decision, what sell, right? And if you think about if you're going to found a company or start something big, the first thing you got to do is that fundamental back of the envelope question, answer that fundamental question on the back of the envelope around a beer with your buddies is, does this make sense? And what would you use to make it all happen? And this is the crux of that, right? Selecting the battery is sort of the first thing that you got to do because you're going to bet the whole company on that technology. This is our old building in San Carlos, making stuff, hook or by crook, coffee on the top of the stove and melting who knows what in the bottom, epoxy potting or something like that, the first team with that mule. And then they kind of got, demonstrated they could do it, figured out how it was going to be, what it was going to look like, and then they got seriously into the design of the Roadster. Oh, so this does address some important things though. So battery packs are expensive. So you're really incentivized to keep that vehicle lightweight and aerodynamic. So some of the two ways that you do that right off the bat are you do an aluminum chassis and a carbon fiber body. The Model S is all aluminum. It's an aluminum body with some aluminum substructure undercarriage. And that's sort of fundamental to, that's one of the ways in which electrics tend to be different. There's a lot of impetus to make internal combustion engine vehicles lightweight as well, but the lever just isn't as strong, right? It's not pushing as hard to bring those things down. Has this big battery pack right behind the seats, power electronics module, and then the motor and drivetrain in the back. I've driven these a few times. We were trying to put some high vibration kind of miles on one that we had made some changes to, and so a bunch of us were driving this one car every day. Twice a day, somebody was making a trip from Palo Alto to Boulder Creek by going up Page Mill, Skyline, Highway 9 to China Grade Road, which is, if you've ever driven on it, is this sort of 1.5 lane road full of potholes, and it's just nasty. I almost got car sick, and I was driving and the whole car was rattling the entire time. But it survived the trip just fine. And boy, it just corners like a dream. And when you decide you want to pass somebody, you think about it, and then you wondered where they went. You know, it's like, wow. Oh, that's those lights in the rearview mirror. Very fast. So in 2006, they unveiled the Roadster in Santa Monica. Big excitement there. Got some stars to show up. And I think it's a lot prettier than the first mule they built. It's very fast. Not a huge top speed, and I think that's really because it's only got one speed. There's no gearbox, right? You got a ton of torque when you put your foot down, but then the motor just basically tops out. It will do 240 miles on a charge, which at the time was, and still today really is a pretty high bar. There's not a lot of other vehicles doing that. I think the Model S may be the only one. And if you ever get a chance to look this up on Wikipedia, because you'll probably be out there buying cars at some time, and you'll want to understand what the heck MPGE actually means. And you have to look it up to understand it, because if I tried to explain it, I'm sure I would get it wrong. But basically, it's telling you how far you could go on the equivalent energy in a gallon of gas. So if a normal car would go 30 miles on a gallon of gas, if it were an electric vehicle, it would probably have about 4 times that, just because the gas engine is about 1/4 of the efficiency of taking power off battery. But you sort of have to look at the details to understand that. Zero emissions, zero gas, obviously. So they started delivering in 2008. I heard this story that when they started, and it's much like it is today at the Fremont factory, the realities of actually building cars, right? So if you build a car and it's got 5,000 or 10,000 parts in it, every one of those parts has a purpose, right? Otherwise it wouldn't be there, which means that you can't ship it unless every one of those parts is in there. We saw this, last year, right, with the earthquake and stuff in Japan, right? The company on the planet that makes door latches for everybody went down, and every car company in the world basically came to a stop for a few weeks because nobody had any door latches. There's only one company that makes them, and they were out of commission. Same thing happens to us. Not door latches, but any number of things. Anytime something is not working, it means that cars start building up in the shop or in the parking lot or wherever until that thing gets resolved, and then they can fix them and send them out the door. And in the very beginning, there was a story about, Elon Musk coming into the factory and seeing 30 cars parked inside, not shipping to customers, and this was the first batch that was going out, and tearing his hair out and telling everybody to get to work and figure out what the heck's going wrong and get these things out the door. It just takes a lot of work to build a car. There's just too many parts. Around the time frame that the Roadster started shipping, because it was getting a lot of press and a lot of attention, Tesla started getting contracts to do powertrain parts for other companies. So Mercedes was one of them, and so they started building the electric. I don't know whether it's just the battery pack or whether there's something more in there. I'm not very familiar with that program, but at least the battery pack in the smart EV is a Tesla part. 2009, they unveiled the Model S. That's when I started in February 2009. So the first thing I started on was, and I worked in the battery pack organization. So the first thing I started working on was the battery pack for the Model S. We got this DOE loan guarantee. We got an investment from Daimler. We got a contract with them for batteries for the A-Class. I don't know if you've seen those around. They're cute little cars. 2010, this was a big deal. They had been struggling with where to build the Model S for a long time. They had a couple of different possibilities. And then with the relationship with Toyota happened. Now, it turned out that the president of Toyota was not a fan of electric cars. He had made a statement like within a year of this relationship saying, Toyota is never going to build an all-electric. This is a dumb idea. And then apparently, either we took a car to Japan or he came over and was in town or something. I suspect somebody flew a car to Japan and took him for a drive in the Roadster. And he got out of the car and was like smiling ear to ear and was like, okay, where do we start? It was really an eye-opening experience. And in fact, after this investment happened, the Fremont factory was owned by Toyota at that time. GM and Toyota had owned it, co-owned it, and then GM had abandoned. Toyota had it, so we picked it up for a song by Bay Area property price standards, and then started working on the RAV4 EV. We've got this great shop at the Deer Creek facility. It's nearby here, and big open floor, and it always just seems to have this random assortment of vehicles in it that have either been built from scratch or converted to electric, and there have been a lot of these RAV4s around, which has been great. They're very cool. In fact, I've heard that of all Toyota's cars, not quite sure if this is right, it's either first or second, but this is the fastest car that Toyota has in terms of acceleration of all their vehicles.
Does that include the Lexus models?
I don't think so. So last year finished the Roadster production, so that's done, and started building the beta fleet. So we've done several iterations of cars, right? Like anything, you're going to prototype, test the heck out of it, refine the design, build another one. Except when you build a car, it just takes a whole lot more effort to build a prototype than I ever would have imagined. You think about stamping a body panel, like big sheet metal panels. How are you going to build a prototype one of those? And yet they do. There are companies, of course, in the Detroit area that specialize in doing this kind of stuff. And just as an aside, that particular technology is they take this, there's some alloy of zinc and tin and aluminum or something, it's called Kurzite. And it's a fairly low melting temperature, very kind of brittle and stiff. But because it's such a low melting temperature, it's easy to recover. So they pour out, and it has very low shrink rate. So they can pour huge blocks of this stuff, machine a shape into it, stamp out a few hundred body panels, and then melt it down and all the shavings that went with it and start over again. So you actually can stamp out these big pieces of stuff. This factory, I'm always stunned when I look, because I have to figure out how to get there sometimes and where I'm going. It's enormous. This picture doesn't do it justice because this line of stuff on the right-hand side, those are the train tracks. There's like 14 or a dozen parallel tracks over here. It's got almost the same amount of train tracks as San Francisco does coming into, feels like. It's a huge facility. Inside, there's 5 million square feet of space, and when it was first available to us and we were kind of wandering around exploring, it felt like a movie set for some post-apocalyptic disaster movie. I mean, it was just this horrible, scary place. You ride your bicycle around with your flashlight, hoping you didn't fall into any one of the number of giant open pits, where there's some giant stamping press had been that they removed. And so these little things down here are all semi-tractor trailers and parking lots full of cars. But a lot of production all the assembly gets done here. A lot of production gets done here. All the stamping presses for bodies, lots of injection molded for big parts like bumpers, right? It's just one big plastic piece for a bumper skin. It's happening in here. So here's one of the presses. I think this is the one, this press can stamp out a piece of sheet metal that's 20 feet long or 15 feet long or something like that. And I think they bought this in Detroit from somebody who didn't need it anymore, and they shipped it out. It's like 100 train car loads of stuff, I don't know how many empty million pounds of material, but they just bang parts out. It's really amazing to watch. So these are doors, door panels. You can see the cutout for the door handle. A couple of years ago, none of this existed. This is all new, and it's just amazing. It always boggles my mind to watch all these robots moving around, doing all this stuff. It's great. I haven't been watching my time. Oh, good. Perfect. Anyway, it's all very cool to watch. It's great to see people are excited working on these because they really feel like they're part of something that's very new. There's definitely some new technologies. I mean, there's lots of new technology in the car that are just sort of car-related stuff. But some of the challenges of manufacturing a car in aluminum, it's just a very different mindset than designing a car out of steel. Form's different. There's different things you can do with it. You can extrude aluminum. You can't really do that with steel. You can easy to cast aluminum. So it changes what the parts end up looking like. Has a similar structure in the rear end to the Roadster. The power electronics. Now the power electronics are sort of a cylindrical module that connects to the battery packs. They all go together. And then the battery pack sits down flat underneath the rest of the car. The parts I designed are the plug, or the socket really, on the back of the battery pack, and the plug that's in the car that connects the two. So every time they put a battery pack into the car, I cross my fingers and cringe. So occasionally it goes badly, and when it does, people get really upset because they're sort of towards the end, right? And now it's my fault that the production has stopped. It's very, very disconcerting. Beautiful car. I actually haven't ridden in a finished one. The only one I ever rode in, I think it had a windshield, but I don't think it had side windows or much of the interior in it when I rode in it. it actually, it got Motor Trend's Car of the Year yesterday. And it got Automobile Magazine's Car of the Year a couple weeks ago. And I think they've all said sort of the same thing, that the body is, yeah, it's nice. It's sort of what you'd expect out of a high-end luxury sedan. But it's really when you start driving the thing that you just get kind of wowed by the feel of it. So if any of you are car buffs, it's funny, I didn't appreciate it when I went to work at Tesla, but most of the people there are sort of car buffs in some way or another. They may not really, it's not like every car in the parking lot is some wacky thing, but there's a lot of them. And then a lot of people who are there, they just really like cars. And so they, everybody loves getting an opportunity to drive one of these. Really fun. There's a test track at the NUMMI facility, so you can actually go around this with the high banked corners and all that stuff, which is very cool. A little scary the first time you go around, but so seats 5 in the kind of normal 2 and 3, and then in the back, under the hatch in the back, there's actually these 2 little car seats for small people. And you can order it with either the 160, 230, or 300 mile driving range. It's expensive. I guess you guessed that. For all the reasons that I talked about in the beginning. And that's really where the opportunities are for the future. The goal of this company was to really make the point and drive it home hard that an electric car could be a real car that people would enjoy driving, right? And the Roadster convinced a lot of people that that was the case, even presidents of car companies, that was the real deal. So the next step is to move down the chain to something a little bit more common. Still, it's a high-end luxury car. But after that will come the next one and the next one, and hopefully this will start the avalanche where all the other companies will get involved. I've heard Elon say, he's not out there to beat everybody. He's happy to beat everybody, but what he wants is not for us to be the only game in town for electrics, but really for this just to be the starting point for electrics. We recently unveiled the Model X, and we're working on the Mercedes B-Class. So Mercedes is going gung-ho on this stuff. Toyota is doing it as well. And we have this new supercharger network, which was one of the questions I think somebody submitted. Here's the B-Class. Model X looks a lot like the Model S, except taller. So it's sort of SUV-ish. These, what do we call these? They're not, we don't call them gull wings though. They had another name for them. It's like the hawk wing, or I'm getting it wrong. I can't remember. Because I haven't seen one of these actually since the unveiling. But these are actually not the front doors that do this, it's the rear doors that do that. The front doors are conventional. So the kids in the back seat are the ones who get the really cool, unique experience. Anyway.
Falcon door.
Falcon, thank you. I knew there was a... this supercharger network was just unveiled. We're starting with facilities in California. So these little circles are your, what range is that? I should be able to guess that from the scale of the map. Must be a couple hundred miles. So California will be well covered. And what you get with the supercharger is, does it say? Oh yeah, 150 miles of range in 30 minutes. So one of the advantages of these lithium-ion cells, especially compared to like lead acid or anything else, is that you can charge them quickly. You can push them hard, and as long as you watch their temperature and stuff, you really can put a lot into them. You can't take them all the way up to full charge, right? Because at the end, if you look at the charging profile for these cells, And I think almost all batteries are this way. The closer you get to 100% full, the more you have to sort of taper off and slow down. So start in California, and then, cover the whole country. Eventually, somebody will be, I don't know who, I heard somebody had already done the coast-to-coast drive in their Model S since they bought it. Somehow, I don't know how they, where they plugged in to do that, but they did it. And when the supercharger network gets really completed, you'll be able to do that faster. So that's one of the ways that and this kind of the supercharging thing is, I would guess this is something that's sort of here to stay, right? If you're going to put 80, 100, 200 kilowatt hours into a car, that's a boatload of energy. So even if the battery technology, actually the more the battery technology gets better, means the faster you'll be able to charge it and the more capacity it will have. So these kind of supercharging things, where you need to be able to dump a lot of energy into them quickly, is only going to increase. You're never going to be able to do this, I can't imagine you'd ever be able to do this at home, right? I mean, you think about how much power you put into your tank at a gas station, it's like a megawatt. You're sitting there pouring gas in, but it's like a megawatt going in there at that rate. It's a huge amount of energy that's going to your tank. Yes, sir?
What are your thoughts on that versus switching out the batteries?
Oh, so there is a company right across the street from us, Better Place, that had talked about doing that. And I gotta say that this is my personal bias. No way. And the reason I say that is not because it's not possible. It's because it's not, I say it because I don't personally believe that it's practical. That getting a bunch of car companies, actually getting a bunch of any companies to agree to a standard form for a battery pack, such that you could remove and replace it quickly, just sounds to me like, I can't even imagine trying to organize that, having that first meeting about, hey, let's do it this way. I want to do it my way. This is going to be beta times VHS times 3/4 inch, it just seems to me like a very difficult problem. You come up with a form factor that people could sort of kind of all go with, like maybe something smaller than the full battery pack, like a module, where some cars might use 2, some might use 6, whatever, and that they were somehow, I don't know, attached to the car in a way that you could really get them on and off easily. There might be a way to make that happen, but I just...
Could Tesla do that with it across its models?
Yes, even Tesla couldn't do that. They could do it across Model X and Model S, because they in fact will use the same battery pack. And we have demonstrated, now, I mean, I say this, there's no way, partially, my job has been to develop the plug and socket between the battery and the car, right? And that is something you can just push together. You shove a battery pack in there, it's connected. You don't have to, almost every other electric vehicle on the planet that's ever been built has had cables going into the battery pack and some sort of bolted joint. Somebody's got to get in there with a wrench and hook those things together. The Model S is the first car, I believe, that actually just uses a plug and socket similar to what your laptop charger uses. It's big. It's about this big. It's got 2 big blades that are, an inch wide and 1/8 of an inch thick. So that part you can do. You can do the quick connection for the high power, the low power signal, because I did both of those, and we've demonstrated it's possible. For the fluid connection, that's also, we call them rapid mate connectors for a fluid and power. And we have demonstrated a quick swap of a Model S battery pack with 4 guys. Nothing really automated, 4 guys with wrenches, and they can swap a pack in under 10 minutes. It doesn't even look like they're working that hard when they do it. And most of the time is spent doing all the bolts on the bottom side. It's, there's 30 odd bolts that they have to take out, and then they drop this whole big pack out on a cart, roll in another one, shove it up there. They do a little alignment to get it right there, and then slam it home and bolt it in place. And they can do it pretty quick, but the piece that I can't wrap my head around is how do you get the companies to organize around a form factor. Yes, ma'am.
So what about, I went to hear Better Place give their pitch, and they were saying, what if we had 4 different types of batteries?
Yeah. So they might be right. I very well could be wrong. It happens daily, so I'm sure that I could be wrong about this one. Yeah.
That's a North American plan. How about the global long-term plan?
I haven't seen maps for that. I don't know what the plan is there.
Isn't there any interest?
Oh, I'm sure there will be. We haven't started selling, for instance, the Model S is not for sale yet in Europe, and it won't be until I finish designing the plug that goes on the outside of the car for the charger to go in. They use 3-phase for all their high power loads in Europe. So it's a different form factor for the plug, and I haven't finished the design for that. Yeah.
We've got 5 minutes left.
Yes, sir.
I actually read somewhere that if you can swap out battery packs and the batteries can be leased instead of bought.
Yes.
So,
that would be
cut the cost.
right. That would be a big deal too. I think that would offset a lot of the initial cost of the vehicle. So yeah, somebody figure that out. Got a way to figure that out?
Oh, I just had another question.
Go ahead.
Well, I have a bunch of questions. For these superchargers, are you guys looking at all into vehicle to grid stuff, or is that not an avenue?
We have a couple of guys who have been looking at that stuff. I don't know what the status of that work is. It does seem like there's a lot of potential there. And this could be like one of those things where there isn't an awesome grid storage system out there yet because it's just too expensive so far. But oh look, people are putting these big battery packs in cars and they're willing to pay the big bucks for them. So yes, the grid storage, this could be how you make that all work. But of course all these things are, there's electronic communication. One of the things that comes with the electric vehicle is you have a communication to the battery. You can talk to it. You can ask it how often it gets used, how much it gets used, what its current state of charge is, whether it likes chocolate or vanilla, anything. It knows all that stuff. And in fact, the Tesla vehicles, if you enable it, Tesla knows all the stuff about your battery pack too, because we have communications with all those things wirelessly. So you really could say, gosh, 2 to 4 o'clock is peak use. Everybody send your power the other way for a couple hours. And
Your battery packs could handle that cycling?
the battery packs could certainly handle the cycling. I think there's challenges of knowing, obviously the owner of the vehicle has to enable that and put some minimum amount of charge they want in their battery when they come out of their office at the end of the day to get home. And so there's a bunch of issues around that. But I think they could take the cycling, and as long as you are careful about that cycling, you get a lot of life out of those battery packs. So I've heard stories about the number of the cycle life of these packs of this particular cell type, really. About if you treat them well, like you only charge them to like 60 or 70% full. You don't actually charge them all the way to max all the time. You don't take them down to the bottom all the time. They actually will take tens of thousands of charge cycles. It's really this top to bottom cycling that just beats the heck out of them. Yes, sir.
What's the end life plan for these battery packs?
I'm sorry?
What's the end life plan for these batteries?
Mostly recycling. It's an aluminum enclosure. The the battery, the cells themselves are actually recyclable, and you can recycle them at a profit. The cells are RoHS compliant. There's no heavy metals or real hazardous wastes in them. So they just grind them up and they can recycle them. Yes, sir.
Sorry, back to the removal battery question. So it can be done with the Roadster, but wouldn't it be feasible for future models to design it in such a way so that it's easier to exchange batteries?
Yeah. You certainly could do it with the Model S.
Right.
And I'm not saying it couldn't technically be done. I think I think you really could. Right now we've got like 30 fasteners to hold the thing in, but obviously if you design another system for attaching the pack, which that could be a challenge.
That's not a high priority right now?
It's not a high priority. There's no place to swap those packs out. It's not in our business model. The leasing thing would be an obvious thing to do, but then what do you buy and what's the state? I think the challenges around the business of making that work are just not something that Tesla's ready to get into yet. Could be, for all I know, they'll announce next week that they're in that business, but I don't imagine that being the case. We've got so many other issues to deal with. You got a question?
Yeah, actually it's nothing to do with the battery or superchargers. It's going back to the cost of Model S.
Yeah.
50 grand. Is Tesla taking a lift out of like the revolution that's happening, the solar financing, where like bringing down the cost of solar installation by just only paying for the energy instead of paying for the solar panels in the first place? Is Tesla kind of sort of like going into a region where they would help the customers finance so that there's like a wide range of adoption and not only just high-end customers who are buying this cars?
Not that I've heard of. I could certainly imagine that sort of thing happening in the future, but it's not where we're at yet. I think they'd still like to turn a profit first. Yeah, we're not running in the red yet, we're not running in the black yet, excuse me. So yeah, we got a ways to go.
On that particular topic, so Tesla burned through a lot of cash with the Roadster, and with it going public and the DOE infusion, is there a projected time frame where you're going to be in the black, or if not, how long do you think?
There is definitely a projected time for when we will be running in the black. I honestly don't know what that is because I didn't think to look it up. And the only data that I would ever be able to give you would be stuff that would be readily available online anyway. So if I knew anything different, I couldn't tell you, and I don't. So I can't tell you anything different. But yeah, I think at some point when our goal is to hit a production rate of about 20,000 vehicles per year for Model S, and it's some point in there we must start running in the black. At some point below 20,000 vehicles per year, we must start running in the black, I'm sure. They just released a press release about that at the quarterly earnings. I think it was 200 a week, just 10,000. I think that was the number. We had a goal. We were trying to hit some threshold, and I kind of think it was 200 a week. But I honestly don't remember I'd have to look at the press release. Anything else? Yes, sir.
Yeah, you can defer this one to your business people if you'd like to. I was looking at sales of electric vehicles and plug-ins, and you're talking under 10,000 units a year. We haven't made a dent in the tons of carbon we're putting in the atmosphere yet. What is it going to take to really make all this stuff take off? Is it the battery issue that you talked about earlier? Is it battery technology, battery cost? how do we get to where there's hundreds of thousands a year it's produced? Not just at Tesla, but I mean industry-wide.
So I'm definitely not the business guy to ask that question. My personal engineering perspective is it's all about the cost. You know, to me, there's cost first, volume second. You know, lugging around whatever it is, 1,000 or 500 kilos of battery payload is too much, and paying $20,000 or $30,000 for a battery pack is too much. So until those numbers really come down, I wouldn't imagine we'll see a really big, but that's pure personal speculation.
Well, let's thank our speakers. That was fabulous.
Thank you.